Hello everyone. Today we are diving into the world of metaheuristic optimization. As its a core, metaheuristic is a higher level procedure or heuristic designed to find, generate or select a heuristic that may provide a sufficient optimal solution to an optimization problem. So it's a kind of master plan designed to guide the search process toward finding optimal solution to complex problems. These problems are typically so challenging that conventional methods either take too long or impractical or simply fail to find the best solution. So the process begins with a set of solutions. Think of them as a different starting point scattered across our landscape, but there is a catch. These initial positions are chosen at random because in the field of complex optimization, starting from a variety of places can prevent us from getting stuck into the local optima, ensuring a better chance of finding a global optimal values. One of the main concepts that metaheuristic depends on is the concept of exploration and exploitation. When we talk about exploration in the metaheuristic algorithm, we are refining to the algorithm's capability to traverse and investigate diverse regions of the search space. Exploration is about casting a wide space. It's the algorithm way of finding the unexplored solution of our search space. The aim here is to seek out and discover new areas that haven't been visited before. It's the algorithm proactive approach to ensure that it doesn't miss out on any hidden values in order to find the global optimum that we are searching for. Why is this important to make exploration? Because if we limit our search space to only familiar solutions, we may find a good solution, a local optimal one, but we could miss out the best solutions. What's important here to understand that the algorithm is not just randomly wandering around. Instead, it's methodically searching through unvisited spaces. It's driven by sophisticated strategy, ensuring it doesn't miss any best solution in order to find the global optimal one. We talk about finding all of the possible solutions through exploration. Now I'm going to talk about exploitation. Exploitation is a critical mechanism of our metaheuristic algorithm. Here we shift out our focus from the broad landscape of potential solution to more targeted approach. Exploitation is all about finding the best solution we have discovered so far. So the goal is not just finding a good one, but finding the best solution. Exploitation requiring a careful balancing to deepen the search without getting stuck into the local optima. By intensifying our search near the promising areas, we are sharpening our solution, refining them bit by bit, and ultimately boosting the algorithm chances of converging the global optimal. There is a main characteristics of metaheuristic optimization algorithm we will talk about now, which they are exploration and exploitation, iterative process, stochastic nature, and adaptability. Let's focus on defining traits of the metaheuristic optimization algorithm, the strategy that give them their problem-solving abilities. First, our strategy of the exploration and exploitation. This algorithm masterfully balance the act of searching the search space for new potentially better solutions through the exploration with the ability of this discovery to extract the best possible one through the exploitation. The second characteristics of the metaheuristic algorithm is their iterative process. The metaheuristic don't just make a single pass through the problem. They cycle through potentially solutions repeatedly, refining and improving them with each iteration. It's a process of continuous evolution and enhancement. Thirdly, we look at their stochastic nature. These algorithms integrate random or probabilistic components. This is not aimless randomness. It's a calculated strategy to prevent the algorithm from getting stuck into local optima, enabling it to navigate more freely and effectively across the search space. And the last characteristics of the metaheuristic algorithm is their adaptability. Metaheuristic algorithms are not built for just one type of problem, with minor to no chances in their core structure. Their adaptability to solve a diverse of optimization challenges exists. There is a lot of meta-heuristic algorithm, and many research is being funded on those algorithms. So we have to understand the categorization of the meta-heuristic algorithm. In our exploration of meta-heuristic algorithm, we see a fascinating reflection of the natural and conceptual world in their design. The categorization of these algorithms are based on the inspiration behind them, demonstrating various sources from which these algorithms draw their problem-solving strategy. So the meta-heuristic algorithm can be categorized into four main categories, which they are the human-based algorithm, evolutionary algorithm, swarm-based algorithm, and the physical-based algorithm. The human-based algorithm are inspired from the human behavior, and the evolutionary algorithm inspired by the nature process of nature selection and biological evolution. Now the swarm-based algorithm is being inspired by the collective behavior of decentralized, self-organized system, particularly animals or insects societies. And about the last one is the physics-based algorithm. The inspiration is based on the principle and the concept of the physics. There is a lot of algorithm that is being included in those categorization, as we can see here. First, we have the human-based algorithm, which include many algorithms. Next, the evolutionary algorithm, which are driven by the principle from the biological world, particularly the process of the natural selection and evolution. In this category, for example, we can see the genetic algorithm, the differential evolution algorithm, and the evolutionary strategy. The third one is the swarm-based algorithm, which are modeled after the collective behavior of decentralized, self-organized system, especially seen in the animal and insect society. This category include, for example, the PSO, particle swarm optimization, the ant colony, the gray wolf optimization, and many other algorithms. And the last one we have see here is the physics-based algorithm, which are drawn from the physical phenomena and the principle, which include, for example, the harmony search algorithm, the artificial chemical reaction optimization, and other algorithms. First, its citations. The foundation paper of the gray wolf optimization algorithm has been cited for more than 14,000 times since its publication in 2014, which speaks volume about its impact and the attention it in importance in the field of optimization. Moving on its application in global optimization, the gray wolf optimization stands out with its strategic design that solves getting stuck into local optima and finding the global optimal solution. These characteristics make the gray wolf optimization an excellent tool for solving a wide range of global optimization problem while finding the best solution. As for the benchmarking, the gray wolf optimization algorithm has been benchmarked against very large of other optimization algorithm, and the result in many cases has been proven and shown that gray wolf optimization has demonstrated a competitive performance, proving its effectiveness in solving complex problems. And the final one is that the gray wolf optimization algorithm is not just another meta-heuristic algorithm. It's So the gray wolf optimization algorithm is inspired from the mechanism of the gray wolf in nature. The first one is from the social behavior, and the second one is from the hunting mechanism. The central to this inspiration is the social hierarchy of the wolf. In nature, a grey wolf organized themselves into a strict hierarchical structure, which the grey wolf optimization algorithm simulates in its operation. The hierarchy is broken down into four categories: alpha, beta, delta, omega, which are the best solution. The alpha are the leader in the context of the algorithm. The alpha wolves are those solutions with the highest fitness scores. The best solution that is being found so far. The beta are the second in command, as we can see in the hierarchy. In Grey Wolf optimization, these are the second best solution, which aid in decision making and guide the other agent. The level 3 is the delta. Delta are the subordinate to alpha and beta, but still hold sway over the omega. They represent the third tier of potential solutions, and the level 4 is the omega. At the bottom of the hierarchy are founded, which follow the lead of the higher ranking wolves. In the algorithm, these represent the rest of the solutions. In the social structure of the grey wolf pack, each wolf has a specific role, and these roles inspire the mechanism within the grey wolf optimization algorithm. At the top, we have the alpha wolves. The alpha are the decision making of the pack, guided the group in activities such as hunting and sleeping. In the Grey Wolf optimization, the alpha solutions are those with the best fitness, directing the search toward optimal regions in the solution space. Just below the alpha, we have the beta wolves, which serve as the advisors. They are the best candidate to replace an alpha and support it by helping with the decision making. In our algorithm, the beta solution are the second best that assist the alpha in leading the search direction. The third one is the delta. The delta wolf are the next in line. If the wolf isn't an alpha or beta, and it's not an omega either, then it falls into the category of the delta. Delta have their own role in the pack hierarchy, and within the Grey Wolf optimization, they represent the third level of solution, offering additional guidance in the search space. So lastly, we have the omega. The omega wolf, these are the lowest ranking members who play an essential role within the pack, such as scouts, elders, hunters. They are also the last to eat. In this context, the Grey Wolf optimization, omega solutions are those that follow the lead of the higher ranked solution, ensuring a comprehensive search across the space. So the diagram in this slides here illustrate the tiered structure of the wolf hierarchy, which is directly translated into the algorithm strategy For navigating the search space to find the optimal solution. Each level of the hierarchy it plays a main role in the gray wolf optimization, ensuring that the algorithm explore and exploit the solution space effectively. The gray wolf optimization algorithm mechanism. We are exploring the core mechanism by which the gray wolf optimization algorithm operates. The gray wolf optimization algorithm simulates the social hierarchy of the gray wolf to optimize a population of possible solutions. And now I will explain how the algorithm works. The algorithm begins by classifying a set of potential solutions into four groups to the hierarchy of walls, as we say the alpha, beta, delta, and omega. These groups are ranked based on the fitness of the solution. The fitness begin with a measure of how good a solution is in the context of our optimization problem. The alpha wolves hold the fittest solution, followed by beta and delta, with omega containing the least fit. As we move to the next generation of solution, the algorithm updates each group of agents according to those first best solution. This process is dynamic and continuous in each iteration, with each new generation refining the search for the optimum. The update mechanism is informed by leading solution, especially the first three best solution from the previous generation, corresponding to the alpha, beta, and delta wolf. The rest of the agents, which they are the omega, adjust their position in the search space based on the position of these leading three. For the inspiration of the gray wolf optimization, we have the hunting mechanism. So in addition to the social hierarchy of the gray wolf optimization algorithm also draw inspiration from the hunting behavior observed from those animals. The algorithm abstracts this behavior into three primary steps, each phase in the optimization process. The first one is tracking the prey. This step represents exploration, much like wolves track the prey. The algorithm explores the search space, seeking out potential regions where the optimal solution could be. The second one is encircling the prey, continuing with exploration characteristics. The wolf often encircles the prey to contain it. Similarly, the algorithm encircles promising solution areas, ensuring a comprehensive search and preventing the escape of any potential optimal solution. And then we have the attacking the prey. This is the final step, is where the exploitation come into play. Once the prey is identified and encircled, the wolf move in and forward it. The gray wolf optimization algorithm mimic this by narrowing down the search in identifying a promise area and intensively fine-tuning the solution to converge on the optimal solution. So we are going deeply into the gray wolf optimization algorithm. We have to understand how the algorithm process work. We talk about the gray wolf optimization algorithm inspiration, from the social hierarchy and the hunting behavior of the gray wolves, and now we are going to talk more systematically through the process and how the algorithm works. We begin in the algorithm by initialization the gray wolf population. This is where we set up the initial solution randomly dispersed through the search space. Next step in the algorithm, we initialize the parameters a caps A and C. These parameters will help in mimicking the hunting behavior of the wolf and are important in the algorithm exploration and exploitation phases. We then calculate the fitness of each search agent. This is where we determine how close each solution or wolf is to optimal solution. The top of the three solutions are identified as X alpha, beta, and delta. And alpha represent the best search agent, and the second one is the beta, the third one is the delta. These are being taken as the best solution, and then we calculate the average for those best solution. The other agents update their position according to the average value of those values. The algorithm enters into a loop that continues for a maximum number of iterations or until a stopping criteria is met. Inside this loop, for each search agent, the agent being updating their position based on the following equation, taking place based on the value of the three best solution. With every iteration, we update the parameter A and C, which are coefficients that control the step size and influence for the leading solution on the rest of the pack. After updating the position, we recalculate the fitness value for all of the search agents to see if they have moved closer to the optimal solution. This iterative process continues incrementally. The iteration counts each time until we reach the end of the condition. Upon completion, the algorithm returns to the X alpha the position of the best search agents, our most optimal solution. So we understand how the gray wolf optimization algorithm works. As we say that the gray wolf optimization algorithm is one of the meta-heuristic algorithm, and it's being based on identifying random values. Note here in this image, in the center we have the three alpha, beta, delta value, which represent the best, second best, and the third best solution, respectively. So it's being surrounded by the omega value, which represent the remaining of the search agent, and the arrow here indicates the movement toward the best solution, representing exploitation where a value is less than 1. This is where our solution narrowing down their search as they get closer to the optimal solution. The algorithm at this stage tend to converge toward the best non-position. On the flip side, the blue arrow here is represent moving outward, represent exploration, where a value is greater than 1. This is where the agent is moving away to search in more diverse direction, ensuring that the algorithm doesn't miss any opportunity that lies outside the immediate position of the current best solution. The mathematical model of the gray wolf optimization algorithm. In this section, we are examining the mathematical model that form the foundation of the gray wolf optimization algorithm for solving different optimization problems. At the top of the algorithm is the alpha value, representing the fittest solution within our algorithm. Just below the alpha, as we say, we find the beta, the delta corresponding to the second and the third solution, respectively. So these leading solutions are being guided for the rest of the agents, which comprise the omega values representing all the candidate solutions. In the guided search, the gray wolf optimization algorithm, the search for the optimal solution is led by the three best solution, alpha, beta, and delta. So they determine the direction and agents of the search, influencing the omega position. The omega don't search independently, but follow the lead of the top three solutions. The diagrams A, B, C, as we can see, visually represent these concepts. The diagram A shows the hierarchy ordering of solutions. The diagram B and C likely illustrate the algorithm update rules and how each omega agents adjust its position relative to the alpha, beta, and delta corresponding to phases of the algorithm where the coefficient A are greater or less than 1. Let's go in details of the mathematical model of the gray wolf optimization algorithm, where we will look at the specific equations that govern how each agent updates its position in the search for the optimal solution. The first equation 3.1 which represents the distance calculation. The distance d is calculated as the absolute difference between the position of the prey, x-prey, and the current position of the gray wolf, xit. This distance will inform how the wolf adjusts its position. The position update is represented in equation 3.2. The new position xit plus 1 for the next iteration is determined by subtracting a portion of the distance d from the current position xit, scaled by the vector a. This equation allows the omega to move either toward the best solution for exploitation or in the opposite side through exploration, depending on the value of A. The coefficient vector A in equation 3.3, the vector A is being calculated here by multiplying the random vector R1 element with 2A and then subtracting them from A. The random vector R1 comprising component randomly sampled from the distribution between 0 and 1. The value of A decreases linearly from 2 to 0 over the course of the iteration, influencing the step of the movement. The coefficient vector C in equation 3.4, similarly the vector C is obtained by multiplying the random vector R2 with 2. This vector introduces a randomness into the movement strategy, contributing to the algorithm. We are focusing on the core of mathematical expression, that the gray wolf optimization algorithm employed to iteratively update the potential solution toward the optimal solution. Each agent updates its distance from the best solution, where d alpha, d beta, d delta are the distance of the alpha, beta, delta from the optimal solution. These distances are calculated using the current position x alpha, x beta, and x delta, and the position of the prey x 0, modulated by the coefficient c. The new position x alpha is found by adjusting the alpha current position toward the best solution, influenced by A alpha and D alpha. Similarly, the position x beta and x delta are updated for the beta and the delta values. The average of these three values updated position give us the new position x vector t plus 1 for the wolf pack at the next iteration as shown in the equation. The formula ensures that each one is influenced by the leading three values, guidelining the agents toward the best one. These updated position allow the algorithm to balance the exploration and exploitation with the agent closing as they progress through iteration. Let's explain more the mathematical model of the gray wolf optimization algorithm equations. First, I will explain the position update equations, and I will explain the coefficient vector equation and the adaptation parameter A small equations, how it's being calculated. The position update equation, the position of each agent for the next iteration t plus 1 is being updated by considering the current position xit and adjusting it toward the optimal solution. So every agent position is being updated according to the position of the three best solutions, where xit plus 1 equal x prey minus a multiplied with d, where the value of the a and d is being calculated according to equations. The coefficient vector equations for the a value and the distance d value is being calculated according to the equation as we can see here. The vector a is defined as a caps equal to multiply with the a vector multiply with the c vector minus the c values, and the distance d is calculated as d is being the absolute value of the c vector multiply with the position of the prey minus the position of the optimal value. A is essentially here serve as a scaling factor for the movement, while the distance d here can ensure that the agent move toward the optimal solution based on the current exploration and exploitation need. And the third equation here is the adaptation parameter small a. This value scale down linearly from 2 to 0 over the iterations t, which show the balance between exploration and exploitation, and the updating value of the a small is being calculated as the equation as we can see here. This linearity of the a value decrement allow the algorithm of the gray wolf to transition from exploration to exploitation as it's being progressed through iterations. In the illustrative example, we have observed the gray wolf optimization algorithm at the initial state of the optimization. On the left side, we have the initial state of the agent represented a two-dimensional search space. The optimal solution is marked with a red dot close to the best solution, which are the most promising solution, the alpha value with the green dot, the beta with the blue dot, and the delta with the purple dot. These are the leading values which direct the rest of the agents. All of the other candidate solution, the omega, are being represented with the black dots. As we move to the right, we see the result of the iteration of the algorithm where the parameter a is equal to 2, suggesting and emphasizing on exploration. The omega value adjust their position based on the movement of the alpha, beta, and delta. Notice how the distribution of the all of the agents is being changed from the initial state. They have spread out, exploring different regions of the search space, avoiding convergence too early in the process. This visual example allows us to see how the algorithm balance the search exploration with the guidance of the leading values. As the algorithm progress with the parameter small a decreasing, we would expect to see the particles converging closely to the best solution, indicating a shift toward exploitation as the solution space is narrowed down. So the value of the A lead the optimization process mechanism. If the value of the A is equal to 2, then we are in the exploration phase. If the value of the A decreasing from 2 to 1, we are going towards the more in the exploitation phase. In the exploration phase, we are trying to find all of the possible solutions, and in the exploitation, we are trying to update the position of the agents according to the optimal solution. So if the value become 1, then we can see we are in the optimization process, and the exploitation process increasingly appear here if we decrease under the value of the 1, and if the variable a equal to 1, this means that the optimization process is at the end and we are in the converging toward the optimal solution. Following the best 3 values of the alpha, beta, and delta, we can see how the omega agents are gathering between the best 3 values around the centroid point between the alpha, beta, and delta, reaching the optimal point. In this example, update the position of all of the agent, and after that we select the new alpha, beta, delta. The convergence of the gray wolf agents might look like as we can see in the image, according to the changing value of the A from 2 to 0. It appears that time has progressed within the gray wolf optimization algorithm. We notice that all of the agents after the position update are now clustered even closer together, a sign that the algorithm has transmitted from exploration to exploitation phase. At this stage, after the update, we would typically select the new alpha, beta, delta poles those closer to the optimal solution. The CEC benchmark function outlines a set of standardization test functions that is being used to evaluate the performance of optimization algorithm. These benchmark functions are categorized into different types based on their characteristics and complexity. They include the unimodal function from function 1 to function 5, the multimodal function, which include the basic function, the expanded function, and the hybrid composition function. As we can see here, the CEC benchmark function is being classified into the unimodal function and the multimodal function. The unimodal function, which include the functions from function 1 to function 5, and the multimodal function, including the functions from function 6 to function 23, for example, here. The unimodal functions, these functions have a single optimal value. They are used to test the exploitation ability of the optimization algorithm because there is only one peak. The multimodal basic function, this category includes the function that is being appear more complex than the unimodal function, which have multiple local optimal values, but are not as complex as the next equations and functions. The multimodal function from function 12 to function 23, these functions have multiple optimal values. They make them more challenging for optimization algorithm because they have to find the global optimal among many local optimal values. They are to test the algorithm ability to avoid the local optima and to explore the search space effectively, trying to find the global optimal values. The expanded function from function 12 to function 14 are more complex version of the multimodal function, designed for further challenging optimization algorithm with even more complex equations. And finally, we have the hybrid composition function. Hybrid composition functions from function 15 to function 20. These are composite functions that combine two or more functions to create a complex landscape with a multitude of local optima. They are used to solve real-world problems and test how well the algorithm can handle complex multimodal landscape. Various unimodal function is shown here. The unimodal function have only, as we say, one peak, maximum value, or one minimal value within the specified domains of the search space, and it focus typically and being used in the optimization to test the exploitation capability of the algorithm, since the goal here we're trying to find a single peak. The CEC benchmark function basic function is shown here from function 6 to function 12, and we can see how the equations becoming more complex more than the unimodal function. For the multimodal function, we have provided a range of mathematical functions which are likely part of the suite of the test problems used for evaluation the performance of computational optimization algorithm. These particular functions appear to be designed to assess how the algorithm perform on complex, nonlinear, and multimodal landscapes. The function parameters is shown in this table, which show the upper bound and the lower bound, the dimension for each function and what is the minimal value. The table lists a series of the benchmark function from function 1 to function 22 with their corresponding upper bound and lower bound dimension of the search space and the non-global minimum if-min values for each function. This table provides the parameter for various benchmark functions used in optimization to evaluate the performance algorithm. The functions parameter provide a summary of the parameters for a series of benchmark function which is likely to use in testing optimization algorithm. Each function has a specific upper bound, lower bound, which define the search space limit for the optimization process, as well as the dimensionality of the problem, which are most functions is 30 here. For instance, function 1 has a search space defined between -100 and 100 in each of the 30 dimensions with a global minimal value of 0. This means that an effective optimization algorithm should arrive at a solution where the function value is 0 or very close to it within the given bounds. Similarly, the function f7, for example, search space is between -1.28 and 1.28 with non-minimal values of 0. Function f2 involve both the sum and the product of absolute values of its variable, so making it challenging for optimization algorithm due to the potential for a steep gradient and a large search space. In the image illustrate the search space for this function, which is bounded within the range of -10 and 10 for both x and y axis. The gray wolf optimization algorithm is being evaluated using the CEC benchmark function. As we said before, that the result of the CEC benchmark function being used for the gray wolf is a competitive result in comparison with other algorithms. So in this slide, we present a comparison of the result obtained by the gray wolf optimization algorithm and the particle swarm optimization algorithm on various unimodal functions. The comparison is based on calculating the average results and the standard deviation for both optimization methods. The average results are likely to represent the closeness of the algorithm output to the function's minimal value. The lower average value are typically better, indicating that the algorithm was more successful at finding the global minimal value of the function, and the standard deviation reflected the variability in the results obtained by each algorithm, with the lower values indicated more consistent performance. In the previous slides, we showed the unimodal functions results, and now this slide shows the result of the multimodal function, presenting comparative performance analysis of the gray wolf optimization algorithm with the particle swarm optimization algorithm across the selection multimodal function labeled from function 8 to function 13.